In this video, we're going to start looking at DC analysis of our bipolar junction transistors. So ultimately, we want to be able to do this because through our DC analysis, we're going to be able to design or analyze to set an appropriate operating point. So for example, if we're wanting to amplify, we want to be in the forward active mode. And so we're going to see this a lot through the following videos and some examples, and even into our following unit, the basic idea is we're doing our DC analysis to determine or to set our operating point. Once we have that fixed, then we can move on to doing our AC analysis. So this is sort of the groundwork for our next unit as well. So let's start by considering a simple common emitter circuit. And so common emitter circuit just means that we have the emitter grounded. Okay, so I've already got that drawn there. So we notice our emitter again is where we have the arrow coming out. We notice we have a base resistor and a battery VBB connected to our base. So we can define some important things in our base emitter loop. So of course we have a base current I sub B, which is going in at our base terminal. We have a base emitter voltage, VBE. And since we're dealing with just DC values, I'm using capital variable, capital subscript. And then on our collector emitter loop, we have our VCC battery, we have an RC resistor, we have, of course, some collector current IC that's going into our transistor, and we have some VCE, which we're going to be interested in as well, and we have our emitter current IE coming out of our transistor where it's indicated by the arrow. As we get more comfortable with this, we're not going to draw these closed loops explicitly. Rather, we'll just have a dot up here for VCC and a resistor for RC. But for the time being, we're still going to use this closed loop notation. So what we want to do is we want to sort of simplify this circuit a little bit. And one way that we can do that is we can sort of redraw our transistor. So we can sort of use an approximate model. And so we can keep in mind, of course, we have our collector node up here, our base node over here, and our emitter node down here. So with that in mind, let's sort of start by coming down here and drawing our three nodes. So let's draw our base node, our collector node, and our emitter node. And so I'll label those in blue as well. So we've got base, collector, and emitter. Okay. So between our base and our emitter, and so let me go ahead and make some assumptions before we redraw this, or state some assumptions rather, that I'm already making in my head, so we want to share with everybody watching here. So what we're going to assume is we're going to assume that this is in the forward active mode. Because again, most of the time when we're using BJTs, that's where we're going to want to be. And so what that means is that our VBB should be great enough to forward bias that base emitter junction. And so we're going to say that VBB is greater than VBE on, and we're essentially going to treat that junction like a diode. We also want our other junction, our BC junction, to be reverse biased. So what that means is that our VCE also needs to be greater than VBE on. So we're going to assume these two things are true such that we're in the forward active mode. So if that's the case, like I was saying, we can treat this base emitter junction like a diode which has been forward biased. So we have something that looks like this, and the voltage drop across this diode is going to be VBE on, which is essentially just the same thing as the cut-in voltage, or V gamma, that we saw in previous units. Now, between our collector and emitter, we can model that as a dependent current source. So this is going to be some current, so our collector current going in this direction, and we know the value of that, again, if we're in this forward active mode, is going to be beta times our base current IB. All right, and from there we just make our external connections that we have up here in the circuit. So for instance, our emitter is grounded, so we can connect this emitter terminal to ground. From our collector terminal, we go through a resistor and a battery, which is grounded on the other side. So we have something that looks like this. And similar thing on our base. So this was our VCC, this was our RC, this is our collector current IC. On our base, we have the resistor RB and the battery VBB. So we have something that looks like this. Okay, VBB and RB. And here is our base current, and then of course coming out of our emitter, we have our emitter current down here. And so just for clarity, let me go ahead and sort of put this in the dashed red lines here. And so what we're saying is we basically remodeled what we had in the dashed red line up here, our BJT transistor, with this forward bias diode and a dependent current source. So what we can do now is we can analyze this circuit here. So let's start by doing a KVL over here on the left side. So let's do a KVL over here. Again, with KVL, we can start at any point, go in any direction. And so with that KVL, what we can say is VBB, so let's see if we can keep it on the screen there. So VBB is equal to IB times RB plus our VBE on. And so we can rearrange that and solve for IB. Why we want to do that, we'll see a little bit later on. So we can say our IB is equal to VBB minus the VBE on divided by RB. And that's going to be useful when we're looking at biasing with a single base resistor a little later. If we do a KVL on the right, so if we come over here and now we do a KVL on this side again, I've just drawn a direction. We could do any direction, start at any point, we'll get the same result. So where we're going to see we have VCC, we have IC times RC, and we have VCE. So I've not labeled VCE, so let me do that here. So of course that's just the voltage between our collector and our emitter. Okay, so doing our KVL on the right side, we have VCC is equal to IC times RC plus that VCE. And so again, we can rearrange this and we can put it in a form that's going to be a little more useful later on, and we can say VCE is equal to VCC minus IC times RC, and we'll actually look at a different form a little later on. So I don't necessarily want to box these in, but let me just circle those because they'll be a little useful, but they're not necessarily crucial for every circuit. Again, this was dependent on the specific circuit configuration we looked at here. So we'll come back to those later. Before we do that, I want to talk about another idea, which is power dissipation in our transistor. So power dissipation in a transistor we'll say is P sub T. And so for the most complete view, we can say that's going to be IB times the VBE on plus IC times VCE. And so if we come back up here to our diagram, essentially what we're saying is we're looking at our IB times this voltage, so power dissipated there, and IC times our VCE, so our power dissipated here. However, remember that we're in forward active, so what that means is our IC is beta times IB, so IC is usually much greater than IB. So we can typically neglect this first term based on our from our base current, and we can say that the power dissipated in a transistor is approximately equal to IC times VCE. And so this equation is not dependent, or rather both of these equations shown on the screen right now are not dependent on the particular circuit. If we have it in whatever configuration, we can find IC and VCE and know the approximate power dissipated in the transistor. So before we come back and look more at these equations and talk about things like load lines and Q points, let's look at a simple example and get some practice finding some of these values.